title in French, la physique quantique, des brumes d'interprétation au dévoilement du sens physique. In English, quantum physics from the mist of interpretation in the unveiling of the physical meaning.
Let me add something. We have talked with him in the last few days. This morning he was here with us, and we can say that most of the ideas he is developing are ideas that are scattered in some of his papers in English and in French, including the chapter on the handbook about Einstein's views. So we invite you to see this chapter, and also we want to add that Michel Paty was very important support to the organization of this conference. That's all.
All right, so we resume. So it's a great pleasure for me to introduce the next speaker, which is Joas. He is also from Copenhagen. So I'll give you the word.
And I'll try to speak up. First of all, thanks to all the organizers, thanks to Oliver first and foremost for putting together this beautiful handbook, and thanks also to some of the previous speakers, most notably Daniela Monaldi and also Helge Krau, because they make my life a little bit easier to talk about here. So my topic today is foundations and applications of creative tension in the early development of quantum mechanics, and it basically boils down to the following question: what role, if any, did applications of quantum mechanics play for the foundations of the theory? And I'm concentrating on the phase from, say, Umdeutung in 1925 until, say, EPR in 1935, so the first 10 years, early quantum mechanics, if you will. There's a tendency to divide the original papers on quantum mechanics into a few categories. So the first one would be proper contributions to the quantum mechanical formulas. Think of the Umdeutung paper, the Bohr and Jordan paper, the Freeman paper, but also Schrödinger's Mitteilung and a few other papers, which sort of are the bare bones of the formalism. Then on top of that, you have some papers which are particularly relevant to the interpretation of this formalism. Think of the Born papers that introduce the probability interpretation. Think of Heisenberg's uncertainty paper. Think of Bohr's Como lecture. Think maybe also of the EPR papers. That leaves a huge pile of papers that few people, if ever, look at, especially among philosophers and physicists nowadays, but also among historians. And that is something that many people refer to as applications of quantum mechanics, very often a subsequent and subsidiary sense, meaning this is simply the further elaboration of quantum mechanics by applying the finished formalism to sort of new empirical areas. So let's quickly look at what these applications consist of. So there's several dimensions of applying the theory. One, the most straightforward one, is the validation of the theory through what one would call with whom problem solving. And here's an early quote from one of the actors of quantum mechanics, Pascual Jordan, who in 1927 wrote, "Simultaneously with the progressive elucidation of the general laws of quantum mechanics, new evidence for the empirical correctness of this theory has been provided by a large number of applications by various authors." And that's a very sort of straightforward, simple element. You apply a new theory in order to establish that it actually gets things out correctly. A second dimension is that you actually want to extend the range of validity of your new formalism by applying the theory to new empirical domains. And here's another quote, also by one of the actors of second generation of quantum mechanicists, Friedrich Hund, a student of Heisenberg's. "With the probability interpretation and transformation theory, the principles of quantum mechanics were by and large known at the end of 1926. Since spring 1926, the Schrödinger equation had been a convenient method for solving the simpler problems, adapted to the mathematical knowledge of physicists at that time. Around 1927, these circumstances led to a flood of applications and the development of practical methods of calculation. And here's a physicist and philosopher commenting on the same. This is Max Jammer. We've already heard from him twice, I think, today. Satisfied that the theory works, since it provided unambiguous answers whenever invoked, physicists engaged themselves rather in solving problems which so far had defied all previous attempts or which promised to open up new avenues of research. The year 1927 thus not only became the year in which the quantum mechanical formalism, in all its essential points, received a formal completion and a consistent interpretation, 1927 also witnessed a veritable avalanche of elaborations and applications of the new conceptions, led to new insights in atomic physics to an unprecedented extent. So far, so good. If these were the two only dimensions of applying a theory, you could say, okay, it's probably justified that people interested in the foundations of quantum mechanics don't spend very much time looking at them. So were applications thus only a flood or avalanche of normal science and problem solving in which an otherwise complete formalism was put to practical use? What I'm going to argue for today is no. There is at least a third dimension of applying a theory which played an important and constitutive role in the history of quantum mechanics, and that is the dimension of applying the theory in order to further articulate, modify, or potentially even overthrow the theory, and for elucidating its meaning and interpretation. All this in the context of application. I don't have a salient quote by one of the actors on that just yet, but I'll of course come with many, many examples in the course of this talk. Let me first comment on something that is crucial to understand in order to understand this role, this sort of productive, functional role of applications. Many actors in the years 1925 to 1927 actually didn't see quantum mechanics as a finished formalism which would survive until today, essentially, right? They expected another imminent radical theoretical shift, another theoretical innovation just around the next corner. And they were sort of looking for domains where they could come up with this shift. Also, one should say that already in the old quantum theory, this had proven a really, really viable strategy of advancing the old quantum theory by extending and clarifying it through applications. We've seen some examples, for instance, from quantum statistics today. So the obvious place to look for an extension of quantum mechanics in those years, and also beyond 1927, was the relativistic extension of quantum mechanics and eventually quantum electrodynamics, the study of the atomic nucleus, but also aperiodic phenomena, the scattering, many body systems, for instance, in atoms and molecules, spin, which was not at the beginning of quantum mechanics integrated into formalism, but had to be painfully integrated into quantum mechanics over time. And quantum statistics were also, as Daniela has shown, the integration basically took until after World War II. So this cut we sometimes make between foundations, very few sort of key papers that we look at as historians and philosophers of the foundations of quantum physics, and these mere applications is artificial and anachronistic. Applications played important functional roles in the development of quantum mechanics into a finished canonized theory, and many of the things I'm going to talk about in the remainder of my talk actually can be found in textbooks and are sort of basic notions that beginners of quantum mechanics are exposed to. Realizing this creative tension between foundations and applications in the actual practice of the actors will also make us broaden our outlook on where to look for actor statements on the foundations and the interpretation of quantum mechanics, I hope. So now here are some examples. I could talk about all of them. I can't, obviously, for reasons of time. But let me quickly mention them. So scattering led to Bohr's probability interpretation. Many particle quantum states, we just discussed that. Simon mentioned the Dirac paper from 1926. The work on complex multi-electron atoms, for instance helium. The work on paramagnetism, in which the Fermi surface sort of appears as an intermediate level concept. Molecular spectra, where tunneling entered through the work of Friedrich Hund. Diatomic molecules, where I would claim with Christoph Lehner and others that Schrödinger came up with a sort of pre-notion of entanglement. The electrical conductivity metals, Sommerfeld, the inclusion of Fermi statistics into the free electron theory of metals, diatomic molecules, for instance, Heisler-London and the theory of the covalent bond, involving again, like in Heisenberg's work on helium exchange forces, molecular structures such as Born-Oppenheimer approximation 1927, ferromagnetism, again, exchange, alpha decay nuclei, again, tunneling, long mean free path of electrons in metals, Bloch waves by Felix Bloch, and I could go on in this list basically until today. So there's new developments in quantum mechanics which not at first sight might be identified as sort of foundational in the same sense as some of the things we've heard about earlier today. But I hope to give you a glimpse by choosing two of these examples at some of these dimensions, at similarities to developments that you're maybe more familiar with. So the first one is scattering. That's something most of you will be quite familiar with because it is the context in which Bohr came up with the probability interpretation. That happened in July 1926. Max Born submitted two papers on quantum mechanics of scattering processes. One was preliminary communication, and the other one was sort of finished thing. They are famous for the introduction of the probability interpretation of the Schrödinger wave function. They're also famous for the fact that only in a note added in proof he would realize that it's the absolute square of the amplitudes and not the amplitudes themselves that constitute the probabilities. And what's really notable about these two papers is that he was not after the interpretation of quantum mechanics when he embarked on his journey towards explaining scattering. And that's something that Marabella famously has shown. This is a quote from a paper by Marabella. She writes, Born's aim in his first collision paper was not to contribute to the clarification of interpretational issues, as his later recollections suggest, but to solve a particular yet crucial scientific problem. The aim of the collision papers was not to argue the reality of particles and indispensability of indeterminism, but rather to describe it theoretically to substantiate Bohr's concept of quantum jumps, the discrete discontinuous energy changes within the atom. Born saw direct evidence for the existence of discrete energy levels in the Foucault's experiments, which he sought to explicate theoretically. So this is an example of somebody who at first might not have had foundational aspirations, but who nevertheless contributed to the foundations of physics in quite an important sense. The second example is Heisenberg in 1926, and this, of course, this development inscribes itself into the bigger history that Daniela actually has talked about. So from Pauli's exclusion principle and Bose-Einstein statistics and Fermi and so on. But sort of, let me just set it up from 1926 onwards. And this is what happened. So right after matrix mechanics, about half a year later, Wolfgang Pauli succeeded in applying matrix mechanics to the hydrogen atom. It's not something that matrix mechanics could do out of the box. It's actually an application of matrix mechanics, if you will. And this happened just weeks before Schrödinger, in a completely different way, could come up with wave mechanics, and thus his theory, if you will, of the hydrogen spectrum. But having explained the hydrogen spectrum didn't help you much in getting to more complex atoms, not even helium. This was absolutely non-trivial, and it took the actors a good part of the year of 1926, and actually only around the end of the year had they figured out, for instance, that Fermi-Dirac statistics was the right statistics and not Bose-Einstein statistics for electrons in atoms. Right? That's something that as late as early November 1926, neither Heisenberg nor Pauli had understood, nor Dirac, and many, many other things. So how did this come about? Well, a crucial paper is one by Werner Heisenberg in June 1926 called Many-Body Problem and Resonance, in which he introduces a new concept, that of resonance, he calls it back in his paper. We today call it exchange, so I chose the term resonant exchange to sort of have both the old and the new term in this expression. And he used that in order to account for the helium spectrum. He made an analogy with a classical picture of coupled oscillators and showed that the helium spectrum split up into two non-combining subsystems, and then you could sort of choose the one that was conforming with Pauli's exclusion principle. And his conclusion, that's a bit later in the year, in the second paper on this topic, is the quantum, and of course you should read it as matrix mechanics, allows for a qualitative description of the spectrum, also of atoms with 2 electrons up to the finest details. What's important to note is that I would claim Heisenberg did not embark on this mission to explain helium merely out of an interest in sort of showing that the range of applicability of quantum mechanics was broader than in his initial matrix mechanics. It was an actual contribution to the interpretational debates with Schrödinger. He wanted to show that his own matrix mechanics was actually epistemologically superior to wave mechanics and led quite naturally to, for instance, the explanation of helium, which had been a long-standing problem already in the old quantum theory. And if you read the paper closely, you find comments to that end where he sort of is very optimistic that despite the equivalence between wave and matrix mechanics, the more productive approach would be his own matrix mechanics. And we have papers by Schrödinger from the same time mirroring this sentiment, stating exactly the same thing on behalf of wave mechanics. This is very surprising. This is J. Robert Oppenheimer, who talks about this sort of invention of the concept of exchange. And he says, I regarded it as a kind of discovery of the meaning of quantum theory. I think that if Heisenberg had found that there wasn't anything new, but just that the integrals of wave functions happened to get the helium spectrum right, it would have been problem solving. It was the fact that there was an element of novelty, this resonant exchange, and something which had never been described before, which turned it from solving a problem to exploring the content and meaning of quantum mechanics. This might be surprising to some of you because people usually might not think of exchange and exchange forces as sort of the crucial new element of quantum mechanics. But at least to one actor, Oppenheimer, it was extremely important. And if you look at the further research program of the Heisenberg group in Leipzig, for instance, then you can actually see that this is a red thread exchange going through their work on electrons in metals, ferromagnets, many, many other physical systems. So why apply? Applications, and this is now sort of statements distilled from my study of the history of quantum mechanics in the years 25 to 35. Applications uncovered avenues for potential extension or even revision of quantum mechanics. They recovered successes of the old quantum theory by integrating them into the new formalism, for instance, quantum statistics. They helped extend the domain of applicability of quantum mechanics far beyond its initially narrow range of application. They contributed to a deeper understanding of what the new quantum mechanical formalism really meant, in a broader sense than the narrow sense of interpretation that we use today, often used today. And in that vein, these applications gave rise to novel, often intermediate level concepts, such as resonant exchange, tunneling, the block wave, spin waves, the Brillouin zone, Fermi surface, and also to techniques of computation, famously Rayleigh-Schrödinger perturbation theory in the context of third communication when Schrödinger was working out the Stark effect in wave mechanics, Slater determinants, Pauli spin matrices as a byproduct of integrating spin into wave mechanics, the Born-Oppenheimer approximation, and many more. The applications thus established the generality of quantum mechanics in practice and not just in theory, and helped bridge the gap between fundamental laws and empirical observations. And here's my conclusions. What I would claim is that instead of reading a few papers over and over again, researchers interested in actors' early stances on foundations and interpretation of quantum mechanics should study more papers by a much broader range of authors, and also more mundane or applied topics such as complex atoms, molecules, or nuclei. Sadly, most of this literature is not available in English. Quite famously, volume 2 of van der Waden's book, Sources on the History of Quantum Mechanics, Sources on Quantum Mechanics, was never published. And if you read the preface to the first volume, he makes a very clear and conscious choice to leave out stuff that he still considers crucial and important, and basically just looks at the sort of matrix mechanics strain of the development. So this might be a reason that these papers very often aren't translated into English, that they receive much less attention. I would claim it's worth looking at them and studying them more closely. Maybe this broadened purview can also help second guess this narrative of an interpretational dark age between, say, 1935 and 1964. Maybe we've just been looking at wrongly at what foundations of physics were to the actors themselves in those years. Maybe they were after something that we don't initially would recognize as foundations. So maybe, I don't know, maybe I shouldn't do that, but let's say interpretation is what physicists think interpretation is. It's not what philosophers or historians think interpretation is to some extent. But so this could also help us face the tasks of future historians looking at the incredibly interesting developments today in quantum information, quantum computing, quantum optics, and so on. These must have some sort of effect on our understanding of quantum mechanics. But to which extent and how do they affect the development of quantum mechanics into a more mature theory? So that would be really interesting, and that's sort of my outlook on which I would like to close. And thank you for your attention. 20 minutes.
Wow. Thank you very much for this fascinating dive into applications in foundations. We have time for questions.
My question is the following one. Do you think that the fact that now quantum mechanics is taught to a much broader group of students, in particular engineers, is going to change the presentation we make of it, or that the approach that people take? Because I think we should also think of the relation between teaching and research.
That is already happening, right? I mean, I've just participated in a course directed towards like early university students, which took an algorithmic approach to quantum information, which is completely different from how I learned quantum mechanics just 20 years ago, or like 15 years ago, I don't know, 20 years ago.
Yeah?
Thank you. Me?
Yeah.
Yeah, thank you very much, Christian. That was a very nice paper. I wonder, so my question is, do you see a similar pattern unfolding for fields like quantum electrodynamics and the stumbling around with nuclear physics? So many of the leading actors at the time expressly said they didn't think quantum mechanics as it presently existed would even apply to the atomic nucleus. And we know now with the discovery of the neutron, suddenly sort of things turned around. But does your story of application sort of having a role in deepening the understanding, does that, do you think, play out in those fields?
Thank you. Yes, absolutely. So as a first remark, it's really intriguing how, for instance, Niels Bohr was willing to give up on causality in individual processes and so on in 1931. So just before sort of the neutron and the neutrino and so on arrived in 1932. So they were really willing to sort of give up a lot of what we believe they would have held as sort of certain truths.
Yeah.
So it was much more fluid, to use a word that Marabella loves to use in this context. And yes, I mean, for one thing, I think we have to reconsider how we write subdisciplinary histories of physics. They're not just sort of derivative histories of how quantum mechanics, like some colonists from quantum mechanics ventured into new fields, brought their skills with them, and then sort of erected new buildings on barren ground in solid-state physics, nuclear physics, particle physics, quantum chemistry, you name it. Right? It's actually much more intertwined with what's happening in sort of mainstream physics, if you want to use that term. And this is also an explanation for why people like, I don't know, Heisenberg work on superconductivity, on, I don't know, strange applications. It wouldn't make sense for them to invest so much time in them if they only did that to sort of churn out numbers that were in agreement with experiments. They're not the guys who would do that. They were after something else. And that's sort of future extensions, maybe pointers to where quantum mechanics was incomplete or could be refined.
Yes.
Thanks for the paper. I have a question about the narrative that you are proposing. I'm very sympathetic to it. I have a question about why do you think in some of the more, I guess, famous papers between, say, Einstein, or in his own correspondence and his own autobiographies, he doesn't go into some of what we would call these more practical or applications, I guess, if you want. Do you have a sense of why some of these authors kind of kept it as a very minimum, just two particles, entangled particles, and that would be basically all of the discussion around it. Do you have a sense about why that is?
Yes, I mean, that's a topic I could talk about for quite a long time. If I gave you the idea that sort of the actors would completely subscribe to everything I just said, I would have given you a wrong idea, because there is very often this distinction between formalism and application, and sort of a positivist attitude, like very famously by Heisenberg in his Umdeutung paper, and somewhere you can say, okay, the way they present it is actually, okay, this is really sort of the foundational core of my ideas, and has nothing to do with the application. But if you look at the actual practice, I'm not so sure about Einstein post-1925, I know too little about that, but of many others, so Schrödinger, for instance, you can totally see that there are sort of these elements of just going somewhere, trying something out. And I mean, one element also that I forgot to sort of highlight is very often it's just about recovering old successes from the old quantum theory. So stuff that had already been explained that now lack an explanation within quantum mechanics. So just recovering that. So for instance, the Bohr and Oppenheimer approximation is actually work by Born and Heisenberg in the old quantum theory, which just gets sort of taken into quantum mechanics by Oppenheimer. And tons of things like that where people really sort of invested, even though in sort of their more systematic accounts of the development of the theory, they would rather sort of support what the received view on application is, which I sort of argue. So that's the tension exactly, which is in my title.
Okay, let's
Thank you.
thank